Hello, my dears. We are on day 11, section 1.7. We're going to talk about symmetry with circles. So there's really four main types of symmetry, but we really work with three. One of them is x-axis, y-axis, origin, and then we have a y equals x symmetry. The best thing about this is you can think of it visually or looking at an equation. So visually, if I'm saying for this first example that I'm x-axis symmetric, that means I'm going to take point A and flip it over the x-axis, and it will land here. It's equidistant from the x-axis. You just flip over the x-axis. As you can guess, for the y-axis, you just flip over the y. Notice it's 2 units away to the right. So to be symmetric, you have to go 2 to the left. Origin, you have to also be symmetric. This one went over 2, up 1. So to be symmetric, you're going to go left 2, down 1, and land right here. When you're symmetric with the line y equals x, it's pretty much just flipping that point based on this line now. So being symmetric, this was up 2 over 1. Same thing, you're going to go up 2 over 1. Really just symmetric from that line. You can flip it over. Here, the origin is just this line, or this point, y-axis and x-axis. If you want to look at it based on the equation, xy, so point A, will now become the same x value, but the y value is negative. It used to be the point 2, 1. Now the new purple point is 2, negative 1. Just the y's change. If your y-axis is symmetric, notice the x's change, but the y's stay the same. The y value is still 1 for both of those points. For origin symmetry, notice both will change. And for this one, when it's y equals x, you just flip the points. This was the point 2, 1. It's now the point 1, 2 in purple. So little symmetries for you. If you want to look at it in terms of the big equation, the thing that changes here is the y value, so the whole function will become negative. For y symmetry, the only thing that changes is x, so that means your input gets changed to negative x. Both for origin get changed, so you'll see it multiple ways. Sometimes people look at it like this, or you may see the negative sign with the y instead of in front of the f of x. Same thing. And here, the x just changes where the y is. So very nice visually and in the equation. We have 3 examples here right now. One of them is y equals x squared, y equals x to the 1/3, and y equals absolute value, x equals absolute value of y. Okay, couples terminology here. Symmetry of this curve here. I'm trying to figure out symmetry. If I had a line through the middle and folded both sides, it would have to match. You can also think of it as a mirror. One side is symmetric to the other in a mirror. So here, you can see that if I did that dashed line on y equals x, so symmetric with the y-axis, this right side, if folded on this line, will match up exactly with that side of the curve. Fun name for this is called even. Is it a function? A function passes the vertical line test. Nice review for us. So if I take this line here and move it through my function, I should not hit 2 values at once. Hey, I don't. So is it a function? Yes, it is. We will talk about the algebraic tests when we get to the back side. What about this symmetry here? Y equals x raised to the 1/3. Well, that is going to be with the origin because the points switch the x and the y change sign. It was 1, 1. Now, -1, -1. This is with the origin. So if I were to sandwich it on the origin, it would match up exactly. We're going to call that odd. Check if it's a function. Let's take our line here and go through. Do I hit two values at once? No, I don't. So yes, it's a function. Here, x equals absolute value of y. If I were to fold this on the x-axis, it would match up perfectly. There's actually no fun name for that one, sorry. And then we check if it's a function. Take our line, we hit 2 points at once. So right at that point, if I hit any 2 points at the same time, it is not a function. A really good picture to look at is right here. This is our starting point, AB. If I reflect it with the y-axis, notice the x value just changes. It just shifts horizontally. If I do x-axis symmetry, notice it shifts down here and changes your y value. So it's the opposite of the axes. So y-axis switches x's. X-axis switches y's. And then origin, just know that everything flips. So this is a very, very good visual, very good thing to have in your noggin as we continue with symmetry. So let's start doing some tests. The graph of y equals f of x contains the point 2, -3. What point must lie on the reflected graph if the graph is reflected first about the y-axis, then we'll go back and we'll reflect it over the x. So these are two separate problems. So, okay, if we are doing y-axis, I'll go here, I'll just zoom up. So y-axis, what value changes? Well, the x. The x changes to its negative. So take our initial point right here. All I need to do is change the x value. Instead of it being 2, it's now -2. Leave the y the same. It still is going on that line, y equals 3, y equals -3. It just moves right and left. What if I did about the x-axis? Well, x-axis, the y value changes to its opposite. Instead of it being 2, -3, it's now 2, +3. Because the opposite of -3 is +3. Now here, what types of symmetry do these exist? This is going to be our algebraic tests. Okay, so this is what we'll be showing when you do your homework, when you do quizzes, tests. All of this algebra needs to be shown because you have to check all the cases. So let's start with A. What type of symmetry does A have? Well, if it is x-axis, so part A, if I am x-axis symmetry, that means the y changes to its opposite. Again, we just talked about that a lot on the front page. Which means if I take my original equation, equals 16, I now have to check, well, would it still be equal if I had a negative y? So instead, if I had this negative y, I'm asking myself, are these still equal? Well, yeah. If you square a negative, it's going to be positive. So these are equal, so I know I'm x-axis symmetry. I'll do a bunch more and then we'll get the hang of it. Let's check if I'm y-axis symmetry. What happens with the y-axis? Oh yeah, the x's change. So I have my original equation. If I change the x to negative x now, is this equation still equal to the one above? Yes, again, due to the fact that if you square a negative, it's always positive. So far I'm x-axis, y-axis. There's one more I need to check, which is origin. For origin, both have to change. X goes to negative x, y goes to negative y. Take your original equation. This is true. We know it's true. And we need to figure out if I change the x value and the y value to its opposite, are these equations still the same? Bet your bottom dollar they are, because of squaring a negative. So overall, for what types of symmetry? You can write out x, y, and origin. You can just say all three. All three symmetries. Part B. Y equals 4x to the 7th minus 3x to the 5th. Oops, that's me attempting it. Let's try if it's x-axis. Again, y goes to negative y. So if this became a negative y, are these two equations the same? Well, no, because this side is exactly the same here, but then one of these is negative. So it is not x-axis symmetry, because those equations are not the same. Let's keep going. Let's keep testing. How about y-axis? X goes to negative x. So I have my original. Oh, don't know why I changed color on you. Sorry about that. So we have our original equation. And now I need to see if I change this to negative x, change this to negative x, are they the same? Well, we were just using the fact if you square a negative, it's the same. But here, I'm raising my negative to an odd power. Any odd power will not give me a positive value. So it's not y-axis. These would be different because the negative is raised to an odd power. Being that it's not x and it's not y, it does not mean that it's not the origin. You still have to check. So we're going to check origin again. Take your original equation. And let's now put negative y and negative x's. Okay, so this one's positive, here it's negative. But this negative and these negatives can cancel and give us the numerator, the top. I don't know why I call it the numerator, the top one. So in reality, these actually are the same. And you can try by plugging in a value. Plug in the 0.11. See if it's true. It is definitely true. Those double negatives will cancel out. So for problem B, it's just the origin. Okay, I'm going to have you attempt part C based on all of these facts. I'll give you a moment. Hopefully you've paused the video and check. These are actually not symmetric with any of them. None. Okay, if I did the x-axis, y-axis, and the origin, those equations will not be the same. If you have questions on this, please make sure you ask. If you got any of those wrong, realize you're raising to an odd power for your x's, and then it might clear up some issues. Okay, last thing we got here. The graph of h is symmetric about the origin. Okay, this is important. Origin. If h of negative 3 is 7, what's h of 3? This is our input-output. So it's saying if I input negative 3, that's my x value, I get out 7. Input, output, x, y. Well, if I'm the origin, I even have it right here, origin, x's change and the y's change. So this would become the point positive 3, negative 7. The question is asking, well, what happens if I have h of 3? What happens if I input 3? Well, I have that right here. I input 3, I get out negative 7. It's a little function notation for you as well to end your symmetry. If you have questions about visual or the algebraic part, please make sure you ask, and I'll see you guys soon.